Now we are going to discuss about the topic normalization in. So we can able to remove that a bill amount from the table. And next one is a Boy's Code normal form. For the Boy's Code normal form, first of all we should know which one is the determinant. If A functionally determines B, or if B is functionally dependent on A, then A gives B. Here A is the determinant. BCNF is table is in BCNF if and only uh, if the only determinants in the table are the candidate keys. So the meaning is the determinant should be candidate keys. And for a Boy's Code normal form, we have taken the simple school table as an example. Here the student name and subject names and teacher names which are available. So what are all the functional dependencies available in this in the above table is given a student and a subject, we can find out a teacher who is teaching the subject. So the first functional dependency is with the help of the student and a subject, we can able to identify the teacher. Given a student and a teacher, we can find out the subject that is being taught by the teacher to the student. So the second functional dependency is with the student and the teacher, we can able to identify the subject taught by the teacher. And the third one is given a teacher, we can find out the subject that the teacher teaches. That is, with the help of a teacher, we can find out the subjects. So the primary key candidates are, that is, candidate keys are, the one of the candidate key is the student comma subject. Another candidate is student comma teacher. Uh, then we can go for the third case. Is teacher a candidate key? It is not, because given a teacher name, we can able to determine the subject but not which student studying that subject. Voice code normal form, we have a table student subject, subject teacher, and the columns are student comma subject and subject comma teacher. And the third one with only with the teacher we can't able to find, so it is not a candidate key, so we can remove it. The next one is the fourth normal form. A table is in fourth normal form if it is in BCNF and doesn't have any independent multi-valued parts of the primary key. Multi-value dependencies MVD is for any two columns A and B. If for a given A, there can be multiple values of B, then MVD exists between A and B. That is, if the MVD exists in a table, then it violates the 4NF. So for fourth normal form, we have taken one example, that is a student table, so which is consisting of student, subject and language. There are two independent immediate facts about the above relationship. A student can study many subjects. For example, Geeta, she'll studying mythology and psychology. And also a student can learn many languages. That is Geeta, who can study the mythology in either in English language or with the okay, in the Hindi language too. So the Gita is studying two subjects and knows two languages. If Gita starts studying a third subject, we need to add two rows in the student table to depict this fact of one for the English language, another for Hindi. So the rule is split the independent multivariate components of the primary key into two tables. That is, one is a student and with a subject name, and another one is a student with a language. If we need to add a new subject for Geeta, we have to add just one row to the student subject table, that is in the first table, but we have to add two rows for this purpose on the to the student table, so that we can able to avoid, so which is shown below. So the fourth normal form, this decomposition reduces redundancy with respect to both the independent multivalued relationships, that is subject and languages. If we need to add a new subject for Geeta, we have to add just one row to the student subject table, but we had to add two rows for this purpose to the student table. The next is the fifth normal form. A table is in fifth normal form, or we can call it as a project join normal form if it is in fourth normal form, and every join dependency in the table is implied by the candidate keys. In 5NF, the decomposition splits the original table into at least three tables. Consider the below table SPL table, that is supplier parts and location table, which is represented as SP and L. The table does have some amount of redundancy. For example, the row S1 P1 occurs twice, but for two different locations L2 and L1. For example, that is S1 P1. This is occurring for the location L2, and also the S1 P1, which is occurring for the location L1 also. So here, if you are going to divide the table into two, that is SP and PL tables, then we'll get a table like this, and then we can able to this type of decomposition is called as a lossy. Why? Because of which supplier supplies which parts, we can able to get it from the first table. Which supplier supply to which location, we can able to get the information from the second table. However, we can't able to determine which supplier which parts to which location, we can't able to get it. So we can prove this by carrying out a natural join on these two tables. So just combine these two tables. So then we are getting these many rows for that after joining them. But our original table, which is consisting of only 4 rows, but after joining these two tables we are getting 5 rows. For example, if you are getting S2 P1, S2 P1, for the P1 location we are getting 2. P1 is L2, S2 P1, L2 is one thing, S2 P1, L1 is another one, S2 P1, L1 is another row. So this is the additional row which is added. So this is which is not in the original table. So it is called as a lossy decomposition. So in order to avoid that, instead of splitting the table into two, at least we have to divide the table into three tables, that is SP, PL and LS tables, like below. For example, this is SP table, PL tables and LS tables. So for that we will get a S1P1, S1P2 and S2P1. So these will come in the first table. S1P1 which is already there, so we can avoid it. Then when we are coming to PL, P1 L2, P2 L1, P1 L1 we can have, then again P1 L1 will come, so we can avoid that the second table. And the third one is LS, L2 S1, L2 S1 is there, and L1 S1 we can have, and third one is L1 S2. L1 S2 is the third table. L1 S1 is already available, so we can avoid that. Then if you are combining these tables, we will get this SPL table, that is the original table. For example, S1 P1, for P1 we will get a L2 here. For L2 we will have an S1. So this row will be considered. So here the S1 and this S1 should be same. So then we can take it. So like that we can do it for every row. We can have it for all the columns here. S1 P1, again P1 is here. So P1 to L1, L1 to we have S1, S1 is there. So then we can add that. Then L1 to S2, then S2 to P1, we can add it like that. So like that we can do it, and we are getting this original table. So this, after joining it, we are getting only the 4 rows, which is equivalent to this S1 P1 L2, S1 P2 L1, S2 P1 L1 and S1 P1 L1, the same we are getting it. So here this is a lossless decomposition. So we have performed the fifth normal form correctly. Thank you.